Let's return to the example that we kind of started off with some time ago. Okay, the interval under the curve y equals 2 minus x squared for x between 0 and 1. We could integrate any function over this interval, obtaining an integral that could be interpreted as a mass, a moment of inertia, a volume, whatever. Let's consider what would happen. Well, let's back up a second. This leads us to an integral from 0 to 1 of an integral from 0 to 2 minus x squared of whatever it is we're trying to integrate, with the inner integral being with respect to y, the outer integral being with respect to x. We probably wouldn't want to do this, but we can ask the question of how we would go about reversing the order of integration. That leads to a complication. I haven't drawn this very well to scale. This one seems to be bigger than this one, but consider this a schematic. But at the point, or along the line y equals 1, if we begin by partitioning y, okay, we want to partition the interval from y equals 0 to y equals 2. We're going to have a different situation between 0 and 1, where x is going to run from 0 to 1, and between y equals 1 and y equals 2, on which interval x runs up to this parabolic curve here. This is going to result in a split description of our interval from y equals 0 to 2. This is easily partitioned. It's just a rectangle. This, well, isn't that difficult to partition either in the y direction, but it's not going to be a rectangle. So we consider what happens if our y sub I star of our y sub j star of our jth y sub interval in this partition happens to lie between 1 and 2. In that case, x is going to run from 0 to this curve, as we've said, so that the x that we get out here is going to have the property that yj star equals 2 minus x squared. Now let's write that down. At the curve, where y equals yj star, we have yj star equals 2 minus x squared, and we have to solve that for x. Well, it's easy enough to solve that for x. We get x equals the square root of plus or minus the square root of 2 minus yj star. This region is the first quadrant, and we can clearly see that in the first quadrant x is positive, so it's going to have to equal plus the square root of 2 minus yj star. So that our description in this part of the region is that x runs from 0 to the square root of 2 minus y sub j. If we want to express the integral of f of xy over the region by partitioning the y interval, then we're going to actually have two integrals. We're going to have an integral where y runs from 0 to 1, and we're going to have another integral where y runs from 1 to 2. We have to have two different integrals because we have two different types of limits on our x. On this part of the interval, where y goes from 0 to 1, x just simply goes from 0 to 1. So we're going to just go from 0 to 1, f of x, y, dx. And our inner integral is going to be very simple in form. Our limits in the integral will be very simple. Between y equals 1 and 2, our x is going to go from 0 to the square root of 2 minus y. So then we're going to have our f of x, y, dx. And as long as our f of x, y is something that's not too difficult to integrate, this is really not a problem. It's just that we have to have two different integrals if we partition in this direction, whereas we just have one integral when we partition in this direction. So for this region, we're probably more economical if we partition the x first and write the integral in this form. But again, if there's good reason, there's no reason not to write it in this form. Each way can have its advantages depending on the situation.